In this video, we're going to discuss Hess's law. So the heat that is released or absorbed from a chemical reaction can generally be determined two ways. We can measure this heat experimentally, and this generally involves calorimetry. So we actually have to perform an experiment and measure the heat absorbed or released. This process can sometimes be difficult, can often be expensive or inconvenient. So this is not always the best or easiest way to determine an enthalpy change for a reaction. Another way is to calculate the heat that's released or absorbed mathematically. We can calculate it from other experimentally determined enthalpy changes. To do this, we use the method called Hess's law. So Hess's law states that if a process, such as a chemical reaction, can be written as the sum of several stepwise processes, the enthalpy change for the total process, the overall reaction, is equal to the sum of the enthalpy changes of the various individual steps. Now that's a bit of a mouthful there. Let's go over an example to help us illustrate that and clarify what we mean by that. So let's say that we were studying the Haber process, which is the production of ammonia from hydrogen and nitrogen, and you were asked to calculate the enthalpy change for this reaction, and we wanted to use Hess's law to do this. Well, to do this, we must be given a bit of information. It is known that this Haber process, this reaction, occurs in two steps, and we know the enthalpy change for each of these steps. So let's say we were given the two steps that make up the Haber process and the enthalpy change for each of these steps. Now, what Hess's law tells us is that if we can add these two reactions together and they add up to give us the overall reaction, then the enthalpy change for the overall reaction is equal to the sum of the individual enthalpy changes for each reaction. So let's work through this one to help illustrate it. So we want to add these two reactions, these two individual steps together to give us the overall reaction. So to do that, let's take a look. We need to get 3 hydrogens, 3 moles of hydrogen on the reactant side. Here we have 2 moles of hydrogen from this one and 1 mole of hydrogen. So these add up to give us 3 moles of hydrogen. We also want to end up with 1 mole of N2 on the reactant side, and we have that here. Finally, on our product side, we want 2 moles of ammonia in the gas form. The phase does matter, so we have that. And notice here, this N2H4, dinitrogen tetrahydride, this appears on the product side here and the reactant side of a different reaction. Something that does that appears in one reaction on one side and another on the other, we call that an intermediate, and we can cancel those out. So that intermediate will not appear in the overall reaction. So if we combine these two reactions, we end up with the overall reaction that we were trying to get. So here we add those two steps, we get this. Now Hess's law tells us that if we do that, then we can add these two enthalpy values together to get the enthalpy value for the overall reaction. So we add these two together and we get negative 92.2 kilojoules. So the enthalpy change for the Haber process, the overall reaction, is negative 92.2 kilojoules. So we can do that mathematically without having to actually perform a complicated calorimetry experiment. Let's take a look at another example which illustrates that sometimes it's not always that straightforward. So we want to calculate the enthalpy value for this reaction that we're given here. And we're given that this reaction occurs in 2 steps, and we're given these 2 steps. So let's see if we can add these 2 reactions together to get the overall reaction. Okay, so here's the overall reaction that we're trying to get. Now if I add these 2 together, I have methane, CH4, and 2 O2s, that's good. But I have liquid water here, and I have gaseous water, water vapor, on the product side. Looking up here, I need H2O liquid on the product side of this reaction. So I have H2O gas here and here, H2O liquid on the reactant side, and I need it on the product side. So what we can do in Hess's law is if we need to, we can flip a reaction around or reverse it. So I'm going to flip this reaction so that the H2O gas is on the reactant side, H2O liquid is on the product side. However, when I flip a reaction, we have to change the sign. When we write a reaction in reverse, the enthalpy change then the sign changes for that enthalpy value. So I need to change this from positive 44 kilojoules to negative 44 because now I'm talking about the reverse reaction. Okay, so here I've flipped this reaction around and now I've changed the sign here. So now I've got H2O liquid on the product side, and that's what I want. See, I need H2O liquid here. But I also notice that I need 2 moles of H2O liquid. So I need to multiply this reaction, the second step, by 2. I can also do that. If I multiply this by 2, though, I also have to do the same thing to the enthalpy value for that reaction. So whatever you do to the reaction, you have to do that same thing to the enthalpy value for that reaction. This is because enthalpy is an extensive property, meaning that the magnitude of the enthalpy value is directly proportional to the amount reacted. So it's an extensive property rather than intensive. So I multiply the enthalpy value by 2 and the reaction by 2. So notice now I have 2 moles of H2O gas, 2 moles of H2O liquid, and I've changed that enthalpy value. Now let's see if these reactions add together. So I've got CH4 on this side, 2 O2s on this side. My 2 H2O gases I've got here and here, those can cancel because again, they're on opposite sides of different reactions. So those cancel out. I end up with CO2 on the product side and 2 H2O liquids. And so that gives me my overall reaction. Now I can add these two enthalpy values together to get the enthalpy value for the overall reaction. Remember sig figs, when we're adding or subtracting, be sure to follow the correct rule for sig figs. So I've got the decimal here to indicate that this is significant to the ones place. So let's have you try one. Pause this video and see if you can calculate the enthalpy change for this overall reaction given these 3 individual steps. Pause the video, write these down, and give it a try. Okay, so we want these 3 reactions to add together to give us this overall reaction. So let's see what we have to do. Well, if I look, this third reaction has C2H4. This third reaction is the only reaction with C2H4. I need that on the reactant side. So I know I have to flip this reaction over. When I flip that reaction, I have to change the sign, remember, for that enthalpy value. So what should we do next? Well, after we've done that, if we look up here at this first reaction, it doesn't matter what order you do this in. This first reaction, I can see that I need, I've got H2, F2, and 2HF. Now this 2HF, I need HF on the product side, and this is the only reaction that has HF, hydrogen fluoride. But I need 4 moles of that. So I need to multiply this reaction by 2 so I get 4 moles of hydrogen fluoride. Okay, so I'm focused on hydrogen fluoride because this is the only reaction that contains that. So I don't have to worry about, like some reactions contain, both of these reactions contain F2. But if I look at HF, this is the only reaction that contains it. I need it on the product side, so I know I don't need to flip it, but I do need 4 moles. So I multiply the reaction and the delta H value by 2. And then also the same thing for the next reaction. If I look at this reaction, on my product side, I have CF4. This is the only reaction, individual step that contains CF4. I need it on the product side, so I don't need to flip it, but I do need 2 moles of CF4. So I multiply this individual step by 2 and the delta H value by 2 as well. Okay, so here I've multiplied those 2 reactions by 2 and changed their delta H values. Now, let's see if they add together. Let's look to see if we have any intermediates that cancel. Our H2, we have 2 moles here, 2 moles here, so those can cancel. And then if we look, we should have this carbon is also an intermediate. So we can cancel out those 2 moles of carbon here and here. Now we should be able to add these 2 together. Let's check. We have 1 mole of C2H4. We need that here. We have 2 and 4, so that gives me 6 moles of fluorine gas. So that's all we have on the reactant side. And over here on the product side, we have 2 moles of CF4 and 4 moles of HF. So now we've manipulated these reactions so they add together to give us our overall reactions. Now we can add these delta H values here together to get the delta H for the overall reaction. And we get, as you can see here, negative 2,486 kilojoules. So let's take a look at one last problem and see if you can calculate the enthalpy change for this overall reaction given these 3 individual steps. Pause the video and give it a try. Okay, so we want these 3 individual steps to add up to our overall reaction. So if I look, I've got NO on the reactant side here, that's good. I've got NO2 on the product side here. I need oxygen, just atomic oxygen, on the reactant side, and this reaction has it on the product side. So I need to flip that reaction around so that I can get O by itself, atomic oxygen, on the reactant side. And when I do that, of course, I have to change the sign for the enthalpy value for that step. Okay. So now I have atomic oxygen here. If I look, I've got O2 gas here, here, and here. I need the O2 gas to cancel, and I've got O3 gas here and here. So I need the O3 gas to cancel. Now I can't flip this reaction or this reaction because I don't want to change the NO or the atomic oxygen. So I need to flip this second step. I need to flip it so I can get O3 on the product side to cancel and O2 on the reactant side to help me cancel. And when I flip it, of course, I have to change the sign for that delta H value. Now, if I look at my overall reaction, I see I have 1 mole of O, atomic oxygen, and here I have 2. So I'm going to multiply this reaction by 1/2, and I could do that. And I'm also going to multiply the delta H value by 1/2. Now, if I multiply this reaction by 1/2, if we look, just kind of do it in our head, if I multiply this by 1/2, I'm going to get 1 mole of O and 1/2 a mole of oxygen here. So 1/2 a mole here and 1/2 a mole here. That gives me, or excuse me, 1/2 a mole here and 1 mole here. I'm going to have 1.5 moles of oxygen, O2 gas, and I need those to cancel. So if I divide this by 2 or multiply by 1/2, then that will give me 1.5 moles of O2 here. So I need to multiply this reaction by 1/2 and this reaction by 1/2. So if I multiply those by 1/2 and multiply the delta H values by 1/2, I get the following values. Now let's see if we can cancel everything. So my O2s, I've got 1 mole, as I said here, and 1/2 mole, so that's 1.5 or 3/2, and that cancels with the 3/2 of oxygen here. Now these O3s, those will cancel also, and I'll end up with NO gas on the reactant side, atomic oxygen on the reactant side, and NO2 on the product side. So now my delta H values should add up to give me the delta H for the overall reaction. Now, if you did this differently, but you got the same value, that's okay. There's more than one way a lot of times to manipulate these, so that's okay. But overall, we should be able to manipulate these to get the overall reaction, and then the delta H value should be negative 304.1 kilojoules. So be sure you understand the basic principles and how to manipulate these reactions in using Hess's law to calculate the delta H value for any reaction.